is known, this voltage is measured in order to calculate the current. When this measurement is performed, the joules in heat can also be figured as I squared R. Occurs in resistance. Resistors always have a temperature coefficient, and their resistance values varies with changes in the temperature. This becomes a source of error. Shunt resistors with low resistance values are used in order to limit this heating. Since the amount of heat generation is proportional to the square of the current, if you were to measure a current that is 10 times larger than a given current, in order to retain the same amount of heat generation, it would be necessary to use a resistor with 1/100th the resistance value. For example, if you look in the green box, for currents of up to 5 ampere, a shunt resistance of 100 milliohms is used. And for currents up to 50 amperes, the shunt resistance is 1 milliohm. As we can see here, heat generation poses serious physical limitations in measuring large currents with the shunt resistor method. Although heating can be limited by decreasing the resistance value, other issues pose challenges, namely frequency characteristics. I mentioned a moment ago that shunt resistor method can be considered in terms of Ohm's law. However, in reality, shunt resistors also include other reactants of inductance L and capacitance C. Those reactance components can be ignored when the resistance value is large. But as this resistance decreases, as in large current measurements, these other reactances become too large to ignore. It becomes necessary to think of the resistor as an LCR circuit. As smaller resistances are used in shunt resistors to try to measure large currents, the L and C components make their effects felt. In these cases, the frequency characteristics deteriorates for both amplitude and phase, making it impossible to accurately measure high frequencies. Based on these facts, we can say that the shunt method is better suited to measuring small currents used in the power consumption of, say, household appliances, rather than in power electronics, where the ability to measure large currents at high frequencies is required. So, generally speaking, a shunt resistance of 1 milliohm for measuring 50 amperes current can only be used at a frequency of up to several kilohertz. So, as to measuring AC power, I mentioned how the amplitude and phase characteristics of shunt resistors deteriorate. So, I'd like to take a moment to review the fundamentals of power measurement. Measuring DC power is simple. It's a simple calculation of current times voltage. However, in AC power or active power, the magnitude of the voltage and current rises and falls in time. This means that power will vary with time. This also means that active power is the average of the product of instantaneous voltage and instantaneous current over time. It can be expressed by the formula shown here. Active power is equivalent to the result of multiplying the RMS voltage, the RMS current, the cosine of theta, and theta represents the voltage current phase difference. Based on this formula, we can see that having accurate amplitude and phase characteristics is an important requirement in order to measure active power accurately. Here is a comparison table of the shunt method and current sensor method. Each method has its own advantages and disadvantages. The key to highly accurate current measurement is choosing the right one by application. This slide shows each measurement method and the amount of current that its correlating amount with its amount of correlating current. Minuscule currents of 1 ampere or less can be measured with high precision across a broad frequency band using the directly wired shunt resistance method. Large currents, however, of 5 amperes or greater can be measured with high precision across a broad frequency band using the DCCT or current sensor methods. For currents of 50 ampere or greater, the current sensor is inevitably best suited. Now that we've seen the benefit of current sensors, let's look at their types and features. Here, we see a summary of the various current sensor types that Hioki develops and sells. Each has its own characteristics. We are confident that Hioki is the only manufacturer in the world that offers such an extensive selection of current sensors. Of all of these current sensors, AC/DC zero flux type flux gate current sensors are ideal for use in high precision power measurement applications. The AC/DC zero flux type can measure DC as well as AC currents using a magnetic detection element, Hall element, or flux gate. Flux gate method, the flux gate model uses a flux gate marked FG in the picture. It detects current, enabling high precision and highly stable performance. More specifically, the flux gate detects DC magnetism. Flux gates have high sensitivity, so much so that they have long been used to observe geomagnetism. One of their outstanding characteristics is that they exhibit almost no offset drift. Consequently, they offer excellent long-term stability and extremely high precision. This type of sensor is ideal for measurement of batteries and inverter power. That is why these are used in combination with power analyzers. There are various designs, even among the AC/DC zero flux type flux gate current sensors. This slide offers a more detailed description of them. They can be divided in two general types: clamp current sensors on the left, which can be opened and closed, and pass-through sensors, which cannot be opened and closed. Clamp sensors can make measurements without cutting the wires being measured, offering a balance between convenience and accuracy. On the other hand, pass-through current sensors, which offer better accuracy and stability, are better suited to applications where there is a need to measure efficiency more accurately, even if the wires need to be cut.